Okay, hi, I'm Lisa Martinez, and the title of my presentation is Determining the Role of Volume Regulated Ion Channel in Astrocyte Volume Reduction by Hyperosmolarization. So the purpose is just to determine whether astrocytic RAC plays a role in astrocytic volume, and the goal is to perform imaging experiments using astrocyte RAC conditional knockout and litter mate control mice within like these 2 days and conditional upon when equipment is available, ideally with an N of 5. However, I do want to note there is limited availability of the rig and lab, so I'll be conducting critical analysis with grad students when it isn't available, which I'll explain later on. So the hypothesis is that if RAC plays a role in astrocytic volume change, then there would be a difference between astrocytic volume when RAC is selectively knocked out. And this is important because what RAC is, it's basically a volume regulated anion channel. It regulates cell volume. It's a stretch activated ion channel. It consists of swelling activated currents. And why we're focusing on this is because there's a specific subunit, which is LRRC8. And this is permeable to excitatory amino acids. Specifically, what we're looking at is glutamate, which is a primary excitatory neurotransmitter when the cell starts to swell. The mouse line that we'll be using is swell GFAP. The reason we are using this mouse line is because it's known to target the knockout of RAC, specifically within astrocytes only. And how it does this is through a Krylov system, which has the gliofibrillary acidic protein. So some background of like why we should all care is it all stems back to epilepsy. So epilepsy affects over 2.4 million people. Unfortunately, 33% of these cases are unresponsive to anti-epileptic drugs. So we wanted to look at the mechanism of epilepsy, and to dig further deeper, we looked at the importance of astrocytes and the mechanism of seizures. So how a seizure happens is within like the astrocytes, specifically once the cell starts swelling, all the astrocytes are clumped together and there is a decrease in the space. So what happens from then is because they're all bumping into each other, that's when it creates like spark for it to be a seizure. So just to wrap up the reasoning is just to understand the role of RAC, because there's not much data about RAC because it is very hard to quantify that data too. To determine its involvement in cell volume reduction, we know that it impacts it, but we don't know to what point it does. And another thing to note about RAC is that it does modulate cell volume bidirectionally. And how we're all going to do this is we're going to use mannitol. So we want to be sure to raise the hyperosmolality without changing the extracellular concentration, so it can be as close as it is to the artificial cerebrospinal fluid. So how do we do this? It's divided into 3 steps. We first have the slice prep. Slice prep is just making sure, bisecting. It's making sure that once you bisect the brain slices, that they're ready to be put into the microscope, and making sure they don't die during the process. Once we do that, then we can actually do the dissection, which is where you dissect the mouse's brain, and then we carry it over for imaging, which we use a software called ImageJ. So for imaging, what we do is once we do the dissection, once we do the slice prep, we put it under microscope. We're going to see on the left photo, that's how it would look like. We want to first identify the dental gyrus, and then from there go to CA1. We do CA1 because on the right image, as you can see, that's where we can see the pyramidal neurons, and that's where we want to really focus on that area because that's where most of the astrocytes are. And we can also detect the health. So the right photo shows them what a healthy cell would look like. So for the imaging process, how it works is if we look at the right image, the one that says A through E. So first, what the program does, it locates the astrocytes, and then kind of like a movie, it kind of like tracks each point of when it starts swelling from like the beginning to the end, and then it converts it from a 2D image to a 3D image, and then we binarize it just so we have more focus on the exact swelling when we do the analysis later. So on the left image, you can see the zooming in into the astrocyte. So from there, this is how it like normally looks like once you capture it. And on the bottom, where you could see the black astrocyte and then the red So that's what we call the region of interest. So from there, once we gather all the data, we want to make sure that for the region of interest that there isn't as much speckling. So in this image specifically, there isn't as much speckling. Second, we want to make sure that's super clear. And the reason we do all of this is because at the end, the program is going to calculate the volume changes. And if there's like a lot of speckling or it isn't clear, the volume changes are not going to be as accurate as we would want it to be. So far for the data I've collected, as you can see on the left one, that is the example of the image I collected for that data set. As you can see, there is a little bit of speckling. However, we did capture the process of the astrocyte as well. So for this particular data set, I've only have collected the VRAC when it's selectively impaired. The highest was N of 4. And again, like the line was still a GFAP. So if you look at the graph on the right, what we start is baseline, which is we just have the normal ACSF or artificial cerebral spinal fluid. So we start here where it's at normal state, and then once we add mannitol, we do expect it to start to swell here, which is it says from ACSF 2 till 40. So how the protocol goes is we first wash the cell with normal ACSF, and then we wash it for about 40 minutes with mannitol. And for mannitol, we take an image within every 5 minutes, as you can see. And then we do expect it to come back to baseline after we wash it with normal ACSF, as you can see for the last 20 minutes. In total, it's a 60-minute protocol. So this is what we expected to see. So what we expected to see is that when we did impair BRAC, that it showed this kind of like data. I do plan for further like thoughts to expect volume to be impaired as BRAC is selectively ablated. Next steps is just focusing on finding the hippocampus faster, because as you can see, the data set was I only managed to get like an N of 4. Ideally, I would want an N of 5 just to have a good data set and so I could be more accurate at volume changes. And second, I guess the struggle I had was troubleshooting data analysis program. Just making sure that the program doesn't have any bugs in it, because it did keep on crashing during the experiment. So just making sure that the program works next time, and maybe just testing it out a few times after experiment as well. And for future research, just to understand the mechanism of epilepsy by observing volume changes when BRAC is ablated. And I would like to thank the Marcus Star Trainee Program, Dr. Ernest Martinez, Rebecca Brown, Dr. Todd Fiacco, the grad students, Erin Walsh, Alex Bilas, and Sandhya Sarem, and my fellow undergraduate students. Thank you.
Thank you so much, Lisa. We really appreciate